So today, what I want to talk about is relations, functions, and that sort of thing. The learning target is I can describe relations as functions, and also I can use function notation and evaluate functions in real context. So the first thing I want to talk about is um, what we talk about is relation. So what is a relation? A relation is basically any ordered pair any ordered pair that you can think of. So you can actually represent it in four ways. You can represent it as a table. You can represent it as what's called a map. You can represent it as a graph, and you can also represent it as like an equation or rule. So what does that look like? So if you're going to do it as a table, it literally is something like, you have an X and a Y. So if you have an X or a Y, like if you have like one, two, say three, and then this is like negative five, zero, and one. And of course, when we say an ordered pair, you can also write it as like one comma negative five, um, 2 comma 0, 3 comma 1. So you can write it, and that's relation. When you talk about a map, I don't know if you've ever seen this before. When they talk about a map, it literally is like if I did like 1, 2, 3, and then over here I have my output negative 5, 0, 1. If I did like 3 going to negative 5, 2 going to 0, 1 going to 1, that's fine. A graph, literally just dots, right? And then like an equation or a rule, you can say something like y equals like x squared plus 3. Yeah, those are all examples of relations. Now, when you have a relation, you have a couple things that you need to know, be aware of. One of them is domain. Domain. Now, what is domain? Domain is, we call this the input. You can call it the x values. Some people call it the independent variable. So you call it the independent variable. That's domain. It's the set of all x's, all inputs. Then the other one, never guess what that is. That's range. Range is equivalent to what we say output. Range is equivalent to output. Range is your y values, right? Is your y values. Typically, we call this the dependent variable. So that's what you have. Okay. So realistically, when you're given the domain and range of stuff, when you're doing things like that, so like in an ordered pair, if I give you something like, I don't know, give you something like 1, 1, 8, 6, and 4 comma 7. If I give you that, that's your ordered pair, or that's your relation right there. Your domain is going to be 1, 8, and 4, and then your range is going to be 1, 6, and 7. So that's your domain, and that is your range, if that makes sense, right? Moving on to if you did by like a graph, if you had a graph, literally, if you had a graph and you're looking at this, I don't know, let's see if we did 1, 2, 3, 4, and we did 1, 2, 3, 4, and 1, 2, 3, 4, and 1, 2, 3, 4. put a dot right here, and I put a dot like right here, and I put a dot like right here. So realistically, your domain, which you use the D, do curly bracket, your domain in this case, I guess if we're looking at this guy, what is this? The domain here would be 1. So I could say it's 1. And then I could say that another domain is going to be, so that's 1. And I guess this is 1.5. 1.5. And then this guy looks like -3. That's my domain. And then my range would be all the outputs, the dependent variables. So my range would looks like it'd be -1, -3, and 2. So -3, -1, and 2. So that's your range for that. The other way you can do this is with mapping. And if you're going to do mapping, I don't know, like if you do this guy right here is your 4, here's your 3, and here's 1. Those are your domain. That's your domain, right? So that's your domain, and then your range if it's 5, 8, 7. So if I did 1 going to 5, 4 going to 7, and 3 going to 8, my domain is literally 4, 3, 1, and my range is literally 5, 8, 7. So it should seem a bit like review, not too difficult, right? So another way you can identify domain and range is through through the graph. So here's a graph right here, and if we wanted to, we could look at it and we can say, all right, well, what's the domain here? And now this is a polynomial. You can see that this goes on forever. So since it goes on forever, because you know you have little arrows right here and right here, the domain is all reals. That's what that means. It can be anything it wants. Now the range. The range, you want to think of the output. So you got to think of actually, if I would put this in, let me back that up. If I want to put this in set notation, if I want to put this in set notation, then I guess it would be x such that x is all reals. And then my range, if you look at my range for this guy, you can look at it goes the range is also all reals, but if it ended, let's assume that, let's just hypothetically saying, let's say that, let's take this part out. Let's take this part out, and I actually made a mistake. So let's just pretend it goes down this way, right? So this part of the graph does not exist. Now, if we look at it, the range, the highest this ever reaches is right here. And if it reaches there, it's 1, 2, 3, 4, 5, 6. That's the highest it reaches. So as interval notate or as set notation, it's going to be y such that y has to be less than or equal to, I guess, 6 in that particular instance right there. Let's look at this one over here. If you come over to this guy's domain. This guy's domain is definitely not all reals. This guy's domain is x such that, and it looks like it starts right here when x is -3. So you would say that x is greater than or equal to -3, and that's the domain. And then the range on this guy, it looks like the lowest it reaches is, according to this graph, -2, and it's all the way over to the right. So then what you would say here is y such that y is greater than or equal to, looks like -2. So that's your domain and range in set notation. Sometimes you can do it in interval notation as well. And if we do it in interval notation, this guy right here, this is an exponential function right here. This is an exponential function. And so realistically, the crazy thing about this guy is that if you look, this goes in both directions forever. It goes this way forever and that way forever. And it's just, you look at the x. So in interval notation, your domain is literally going to be all reals, right? And you write it like that. Now the range is a little different. You can see it looks like the range, it looks like it's approaching what is it? That's 1 and that's 2. This guy looks like it's a horizontal asymptote at x equals 2 or at y equals 2. So you would say that its range is it can't be anything, it can't go anything lower than that, but it can't be it. So I'm going to say it's -2 to infinity. But now I'm just assuming that I can't zoom in, but we're just going to say that that's exactly what it is. Um, anyways, is that this next one, this fourth graph, this is actually what's called a piecewise function, and we'll get more into what that is. But a piecewise function, basically, it's a piece here and it's a piece there. But I want to modify this a little bit. I want to make this a solid dot just to make our interval notation good. So our domain in this guy, it really is, it goes this way forever and it goes that way forever. So as a piecewise function, um, my domain is actually, hold on, I want to modify this. I'm going to modify this. I'm going to take this part away. I'm going to put an open circle right here. And I'm going to say that this open circle is at like looks like -3. If I have it like that, where you can see that it can't be -3 and it goes here, it's solid, but then it jumps here and it goes down, my range, or excuse me, my domain is going to be -3 to infinity because it can be anything. And then my range, again, if I'm using this little dot right here and this guy, my range in this, say this is like a 4. I'm just going to count it as like 1, 2, 3, 4 ticks. This is a bad example that I have, but let's say it's 4 ticks. My range is anything smaller than 4, but it can't be 4 because of the open. So I'm going to say my range is from negative infinity to -4, if that makes sense. Piecewises are a little bit weird. It takes a little bit getting used to them, but it is what it is. Now let's talk about a function. Let's talk about a function. Now, what is a function? A function, a function is just a fancy, a function is just a fancy relation. What it is, it's a relation. It's a relation that passes the vertical line test. You guys remember that? The domain, the true definition is the domain is paired with exactly, I would underline exactly one element of the range. So that's what a function is. A function is a relation that passes the vertical line test. The domain is paired with exactly one element of the range. Now you can look, and there's a lot of ways you can do this. What I tell people is if you look like examples, when you look at the like a table, like here's a function x, y. Here's 1, 2, 3, and I got like 4. And if I got 0, 8, 7, 6, look at your x's. Do they repeat? No, we're good. It's great. X's do not repeat, they're good. Another example, so that's a function. Here's another one. If I did something like -2, 0, 2, and then I get 4, 0, 4. This is also a function. It's okay that my y's repeat. It's totally fine. Coming from a mapping standpoint, if I have something like -2, 0, 4, my output value is 0 and 4. If you can see, -2 goes to 4, 0 goes to 0, and that's, sorry, 2, and 2 goes to 4. It's okay that you can see that it says that each domain is paired with exactly one element. So my x's are 1, 1, and it goes to 1. I can't pick two different ones. Another thing is if you had an ordered pair, like if you, I don't know, let's say if we had something like 1 comma 1, and then we had 1 comma 1, we had -5 comma 6, and we had 0 comma 8. these guys are all these guys. This is a function. It's no doubt. We're easy with that, right? Another example, and I'm going to go kind of quick here, is talking about if you go like look at the vertical line test. If you look at the vertical line test, um, if you have a graph like, oh, I don't know, um, say I have a graph like this, and I have the function like that. Is that, or a graph like that, is that a function? It absolutely is, because if you run a vertical line anywhere down it, here or there, it only touches it one time. So that's definitely a function. Something like this, if I graph this guy right here, is that guy a function? Well, no, it's definitely not a function, because right here it fails the vertical line test. It touches it in two locations. What about this graph? That too is also a function, because it passes the vertical line test. So we have that. So there is that. So that's covering some. That's kind of like review of what we had to talk about. Some other things I want to talk about is something called explicit equations, right? Versus what they call implicit equations. Now, what is the difference between those? Now, the difference between it is, so for explicit, this is basically, solved for a variable. So explicit is solved for a variable, like um like it's solved for a variable, so it's like y equals 4x plus 8. Or if you have something like um x equals the cube root of y minus 8. Those are explicitly solved for something. Implicit equations are not solved for a variable. So like one that you haven't seen in a while, x squared plus y squared equals 8. That's the equation for a circle. Something like xy equals 7. 4x plus 2y equals 9. Those are all examples of implicit equations, things that you need to solve a variable for. The last thing we're going to talk about, the very last thing that we're going to touch on, is something called function notation. Now, what is function notation? What is that? That function notation is real easy. It looks like this. It's f in a parenthesis of x. This is red. F of x. All it does is it's legitimately, you might see this, f of x equals y. It basically replaces the letter y. It's the exact same thing. The only cool thing about it is that if you have the f of x or the g of x or the h of x, that it's basically saying that that equation now is definitely a function, so you know it passes the vertical line test. So if I have something like literally y equals 3x squared plus 5, that's like little kid stuff. We typically in advanced math write it as the function 3x squared plus 5. It literally means the exact same thing. So sometimes what will happen is they'll say evaluate a function. So you guys remember, like, we had something like f of -5. Well, do you see that's taking the place of the variable x? So you literally replace it. So 3, you put in a -5 here, plus 5, and you square it. So -5 squared is 25, times 3 is 75, plus 5, and that equals 80. So when you input -5, you get an output of 80. That's all fine. What about the same function? If we have f of x equals 3x squared plus 5, and I want you to find the f of 2a plus 6. That literally means that you plug in anywhere you see the letter X, you put in this entire stuff that's in the parentheses. So then that is a 3, and then this is like a trinomial. Do you guys remember square the first term? That's 4a squared. Square the last term, that's 36. Multiply those two terms together right here. 2a and 6 is 12. So that's plus 24a. And if you don't do that, you have to FOIL it out. So now we got 12a squared plus whatever 3 times 24 is. That's something you probably need a calculator for, but that's 72a plus 3 times 36, that's 108. And then we're going to add 5, and you can finish this out by saying it is 12a squared plus 72a plus 113. That is what happens when you input the expression 2a plus 6 into the formula. So it's not that difficult. There's one last thing that we talk about, and that is getting the outputs from the graph. So the last thing is we have this parabola, and if I wanted to find f of 1 on the graph, what I literally have to do is I go over here, and here's like looks 1 2 3 4 5 1. Click right here, looks like it's -2. So if I do that, I get -2. Then if I have to find like f of 0, then I go to 0 on the input, and it looks like that's -4. And if I want to find like f of 1, f of -1. Then I go over here to -1, it looks like it's 1 2 3. So it's -3. Did I goof that up? When I go to 1, 1 2 3, that's actually supposed to be -3 as well. So that's kind of, it took a little while. I'm sorry it was 22 minutes, but it's been a minute since we've done it, and hopefully this makes sense. I look forward to seeing you in class, and may the force be with you.